Good morning, everyone. I'm usually on UTC time. This is UTC -8. I'll be presenting about the high-performance networking. And if this works, it does, I can step away. And my name is Maciek, long name for Anglophonics. I'm a European. I'm gonna stay so after Brexit. And I'm a lead of FD.io assisted project, focusing on benchmarking and good engineering practices. And I'm distinguished engineer at Cisco, and I'm representing actually a assisted project. So there's few of people here. Sirshak, you've already met. Peter in a row, and also we are the guys who actually are using and testing and trying to break FD.io-VPP, and there are quite a few people here. Now, I am a great believer in collaboration, and that's why there are a few bands here, like Jimi Hendrix from Seattle, Led Zeppelin from where I live, England, and Zoe, a new band, which actually started in Scotland. They came from Australia, the Aborigine guys, and they just won a lot of awards in Scotland and about to invade the world. So I wanted to ask for some, let me just start my timer. And by the way, this is showing 13 minutes. Am I already 30 minutes in my time, Heather? Mm-hmm. This timer is wrong. So you could reset it?
We were a couple minutes behind. I think you're 3 minutes into your presentation.
But not 7.
Yeah, let's reset it to
Right. I have a banana in my pocket. And I also have, if somebody throws insects at me, I have an insect thing. I'm going to take off my jacket when the technical things are being sorted. So let's go. Oh, I believe in collaboration. This is a human hand. This is machine hand. Disclaimer, we're going to be talking about data. And let's see how the data goes. The data is all published, but it is specific to hardware and software tested, and of course a location, like temperature of the lab, which we don't control. Internet megatrends. I'm going to skip through the few of those slides quickly, if you don't mind. They are quite naughty, but I wanted to make sure I pick up on a few points. Cloud, connecting NFV and SDN. But what really makes it click is cloud-native designs. And what really, really, really makes it click is the collaboration in open source. So I'm a strong believer in open source platforms. I was supposed to ask you a few questions before, but the cues were not given. I'm going to ask you the questions a bit later about collaboration and what different organizations like Intel Corporation and Led Zeppelin, the band, have in common. I would like to take you a bit of the memory lane, Moore's Law. This graphic is copied from the Ray Kurzweil book, The Singularity is Near, When Humans Transcend Biology. But I just find it very convenient to present the point I wanted to make, which is the calculations per second per $1,000, they've been increasing, $1,000, right? And there is a lot of things. 1965, Intel founded 1968. But to make it happen, there are a few other folks that were working hard at it. Mr. Boole, Boolean logic, and Mr. Leibniz inventing binary code. So that's 1600. Going forward, the question is the work that this guy started actually still progressing at this really exponential speed? And a lot of people are questioning if Moore's Law is still at work. Silicon Road is ending, and nobody knows what's next, right? So to really know what's next, one should look at this little thing, and I know it's very hard to read, but it says, about members. Do you want to save computing history? Save, don't save, cancel. I'll come back to that. 2017, Intel launches Xeon Skylake. FD.io is part of it. We were part of the launching party. There is a video there. You can click on it, you can watch it. Terabit software data plane. It rocked. So the answer is, does it really work? Yes, it surely does. Ramble on, and if it wouldn't be audio difficulties, we would actually play a Led Zeppelin song here. So some data points on what we have experienced moving from Broadwells to Skylakes. And for any questions afterwards, the team is available, I'm available. Ask and grill us on anything and everything down to electrons and photons. Two-socket server, what is important for packet performance processing, processor, CPU cores, memory bandwidth, I/O bandwidth, intersocket. We are currently not testing intersocket. We're counting cycles per packet, we're counting throughput, as ITF does, and networking guys, and bandwidth. So how do things improved? Moving from Broadwell to Skylake. We couldn't believe our eyes because we saw Moore's law working. Okay. I/O, boom, 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 boom. You will see later comparisons. It's all in open source. Again, the prototype testing on some CRB boards was launched with Intel Skylakes and also MWC last year. Now we have all of this data running in the labs, clicking. Okay? Hundreds and hundreds and hundreds of tests executed multiple times a day. You'll see the graphs in a moment. To understand this, you would need to really deep dive into the paper, a technical paper. We wrote a paper together with Intel. We presented at the KubeCon Austin last year. Some of you were here, so thank you for coming back. We did it on Broadwell. We were hoping to release a Skylake, but we got stopped by some branding police. And the tests are repeated with Meltdown and Spectre. So, the paper should be out before 31st of December, or I'm out of the paper. So, open source benchmarking, guiding principles. Before we go into data, and I have 12 minutes and 5 seconds, 4 seconds, 3 seconds to go. We want to really benchmark this stuff in the open. I've been doing it for quite a few years, and it's very hard, and also working with service providers, very hard to distinguish on what's A, what's B. To the questions asked earlier, how do you compare? How do you compare apples to apples? How do you avoid the situation where you end up with the Cezanne painting apples and oranges all the time, right, from the distance? It's only when you come close at inspection, you see there's actually lots of apples and oranges. Shit. So what we do? We discover the limits and know them. I've been benchmarking Cisco routers, Juniper routers, Alcatel routers, Telabs routers, many other vendors for working for different vendors and competitive and just understanding in customer labs since 1999. In fact, since 1995 when I started working for Crosscom in Gdańsk. And there was somebody here presenting from Intel that previously was many companies before the guys ended up in Intel. And that's what we always did. Find the limits, and then understand them, and then work out the deterministic range. Home calling. ET. We assess on externally measured data, black box, black box, black box. That's what benchmarking working group does in ITF. I don't care what's stuff on the hood. It's a black box tests. Now, to really close the loop, we want the white box, so we actually do the white box, and we'll show you how we are driving IETF standardization in that regard. And we then want to provide feedback loop to the community. Users, testers, coders, everybody. One should understand the laws of physics and use them efficiently. This is my free form quote from Richard Feynman, the physics guy. So, lots of opinions. And that's why I wanted to leave the questions till the end, because I'm going to show some results. They are representative to what's in the lab, including the temperature, including the geolocation. Okay? We haven't found the evidence for cosmic rays. We did find an evidence for temperature fluctuations and various other things. Okay? So very quick speedy review of what CISIT is. We release every VPP release, and we generate reports, comparisons, and so on. There will be more and more and more and more data. Okay? This is an email. If you're on the mailing list, or are you one of those behind one of those bots that are clicking on those links, as we're monitoring them with Bitly, and we know there are bots, then everything is at this link. This is your first point of call. Let us know how browsable it is and how easy to use it is. Painting 780 graphs and making it consumable for humans is hard. We have two types of testbeds, physical testbeds, 3-node, 2-node. We have Xeon Skylakes, Xeon Haswells. We have Atom Denverton. What I haven't shown here, because they are not in operation, or sort of actually both Denvertons and ARMs are still being built. And, but we have Atom 2 nodes too, and there are different links. These are the logical test beds. The display resolution, unfortunately, is well behind my laptop, so you can't blame me for not reading the graphics. I think those projectors need upgrading. But we basically test NIC to NIC through the VMs, through containers in 3-node and 2-node. And 2-node, really, we test the system. 3-node, we can emulate the network, the consumer side, the producer side. We're going to keep the 3 nodes. So I have 8 minutes left. These are just numbers, lots of graphs, lots of tests, breadth, depth, repeatability. Thank you, Ray, for putting together this slide. I keep bulldozing it and updating it. Lots of graphs. So a few graphs. This is what you see when you click on those links. This is the non-drop, zero-packet drop performance of IP4 routing on a single core. You get basic stuff over 18 million TPS. Not bad on Skylake. And this is L2 switching with some cross-connect over 25 million TPS. Okay? This is referenceable data, but this is informative data. This is not normative data. It's tested in the lab. You can see it yourself. You can dig in for the test case, for the code. Everything is open source. Linear scaling. We do scale linearly, although here we are limited by the 10 gig. But as you can see, we will be comparing against the line. And going forward, we'll have a telemetry to explain why it is not Amdahl's law linear. And here's the comparison. Skylake versus Broadwell. 81% faster, 72% faster, 67% faster, and so on. Check a link. It's all there. So now I have 6 minutes, 7 minutes on this NFV sysid stuff, VNF versus CNF. So I'm going to speed up a bit. But we have a problem, and benchmarking is hard and comparison. So we decided to, we have been actually invited by CNCF team to compare CNFs versus VNFs, and we actually don't like comparisons like that. That's why we call it, later you will see, it's actually VNF and CNF. It's a technology and technology. So this is, warning, this is very fresh, and it is technology comparison. Or actually, it's not really a comparison, it's more of the contrasting than comparison. It's not versus. They're both valid, and they're going to be here for a while. But the numbers are fresh, and this is definitely not a product. So it's a soft launch. So I'll have to skip quickly through those. How do you compare those technologies? You don't compare them standalone. You compare them connected. And then you need to work out how you connect them. Taylor already briefed you on what VNFs are good at and what CNFs are good at. So this actually illustrates is the result of the collaboration cross-project. What you will see here is some embryonic version of the new IETF benchmarking workgroup draft that is in the works, that we'll be publishing probably around the January timeframe, and we'll be presenting in Prague in March. NFV note, NFs, VNFs, CNFs. Going forward, we want to apply this methodology to NFs of any kind, software. And the host data plane can be also pretty much anything. User mode software switch, which we're testing, but also Linux kernel mode, direct virtual functions, physical functions, and so on. So we defined this sort of service abstraction. At the bottom is network topology, how devices and functions are connected. Then there is a service topology, how those devices and their functions are configured. And then how they actually forward traffic, service forwarding graph. We're gonna packets. We're gonna focus on the forwarding graph and service topology, and Taylor has already briefed you and used the naming, but we are trying to normalize the naming. So we have basically a VSC, a VNF service chain, which is going the snake forwarding, CNF service chain, snake forwarding, and then CNF service type pipeline forwarding, where we don't touch the host plane, we just enter the pipeline, go through. The way we're testing it, L2, this guy does L2 switching. These guys do IP. L2 square, IP a nice, scalable fib lookup tree. I'm an IP guy. So how do we do it? Service matrix, we create one. You can see rows is network of service number of network service instances. Columns are a number of NFs in each instance. 10 by 10, nice number. 1 here, 100 here. So this is one service with 1, 2, 4, 6, 8, or 10 NFs. This is 10 services, each with 1, 10, 2, 20, and so on, 100. All in a GitHub, check it out. We have some complicated maths, but it's still a linear oversubscription. And for the basic tests where we don't oversubscribe, 100 NFs requires 150 cores. We are still looking for processor to get one. Intel, ARM, NVIDIA, give us one. Results. 3 minutes to go. 3 minutes to go. OK. I can't dwell on the slide because I have 3 minutes to go. But you can see visually, these are the numbers. They are sort of, again, low resolution. But the higher, the better. This is a PPS, 64-byte, maximum receive rate. Maximum you can get out of the socket. The cores. And unfortunately, I didn't run out of time to show you how filled up the socket is. But the higher the density, the more filled up it is. So you can see this is sort of OK. This is sort of better. This is sort of cool. OK? Basic laws of physics. So what we're going to do going forward? Well, work in progress. We're going to ship it in 1901. Pay attention. End of Jan. It will be all automatically executed, thousands and thousands of tests. Peter and the team are hard working at it, right, Peter? Here we go. Affirm, yes. We're going to continue collaboration with an SM team. That's a Spider. And I think Ed will talk to you about the Spider. And then the CI team, Taylor. And we're going to also add NSM into the stuff. And after the soft launch, of course, we're going to go with a hard launch. Now, what else we want to do? I told you about those NFs, right? There is this super duper tsunami of new things. New thinner VMs, micro VMs, nano VMs, pico VMs, feta VMs, whatever, OK? So Firecracker, we're going to give it a go. Then there is this more secure and faster containers, singularity containers. Check out the Git, OK? They are more secure, they say, and they also faster, they say. They're currently not touching network I/O. We want to make them so. Going forward, ITF. We have 2 drafts in works. The first one is for deterministic network devices. The second one is for non-deterministic network devices. This is a faster binary search. This is a mind-boggling, biased theorem, biased inference-based, AI-like searcher finding the point in which device works as advertised. And we've contributed to etcnv. I keep forgetting the number. And this will be the new draft. It's got my name, so nobody will steal it. And then we're doing some RFCs. And that's pretty much, I have 30 seconds to go. So packet vectors are good for you. Okay? I have a vector in my bag. It's not a VPP, but it's an AI Anki robot. We're going to play with it later. It's called vector for a reason. They're using vector things, instructions to make it cool. And then even the kernel guys, David Miller, likes VP. This is a slide from Jerome. This really beautifully summarizes what a proper, modern, physics and ethics compliant modern software network data plane is. Efficient, fast, using least energy. This is the demo I told you about. Click on it, keep the counters going. Look for the violin crescendo that towards the end emphasizes the Moore's law. So we talk about that. Hopefully you see it working. And now it's going to be a few clicks until I get to the final slide. And we haven't updated the slide for over a year now. It still works. And I have 40 seconds to go. It's increasing now. Some references. Yeah, I'm done. These are the project links I copied from Taylor. Thank you, Taylor. CNFCI. And I have one more final slide. Okay. Seattle rocks. So, I would like to encourage you to enjoy Seattle, where FD.io doc will be chasing this little spider, Fayette. FD.io will be underpinned by a very close, open source-based collaboration between humans and humans, humans and machines and machines. And if you don't believe me, go here, okay? They show really cool stuff. And go to the terminal, play with a toad, play with a PDP 10s. They are there, they're online, okay? And you understand why it works. And of course, if it's not Boeing, I'm not going. I picked it up during the charity race yesterday, Christmas. Like you can see, I met Santa. And then I met Bruce. Bruce does something very interesting. Bruce actually has a Cray computer, and he's playing with the Cray, but he says he has a problem with the Cray, right? That's why I have this thing here. And he can't start it. Do you know why can't he start it? It's all plugged in, and he cannot start it. Does anybody know why Bruce cannot start Cray computer, fully functional, Cray, under Cray maintenance, in this beautiful building that late Paul Allen built? Does anybody know?
There's not an on switch.
No. Huh? Power. How much power does Cray need as an absolute minimum?
A lot.
Okay, a lot. What's a lot? Okay, it's 150 kilowatts. Okay, it's going to cost them $1 million to wire it up. So, watching power is important to get performance, right? And that's why counting the clock cycles is equally important. Because once you do that, then the shit just rocks. And that's what FD.io VPP not only claims, but that's what we actually measure. Thank you.